In 3D concrete printing, the material is extruded directly into the open air. There are no wooden or steel formworks to hold the wet mixture in place or protect it from the environment while it cures. That immediate exposure creates a mechanical vulnerability at the exact point where two layers meet. Because the bottom layer undergoes partial hydration before the next layer is deposited, the interface between them is inherently weaker than the bulk material. When printed structures fail, they typically tear apart right at this failing interface. To measure the exact threshold of that failure, engineers rely on the splitting tensile test. A compressive load is applied perpendicularly to the interface. The pressure increases until the maximum stress is reached, forcing the layers to physically separate along the contact surface. Interlayer delamination is rarely caused by a simple printing error or a physical gap in the extrusion. These fractures are mechanically driven by differential shrinkage. Scaling additive construction requires moving past geometry alone. Engineers must treat the physical chemistry of how concrete shrinks as the primary determinant of load-bearing capacity. To study these shrinkage dynamics outside of small lab samples, researchers constructed 3 experimental walls, each 3 meters long and 2 meters high, using distinct concrete mixtures labeled M.01, M.02, and M.03. During the extrusion process, strain gauges were embedded directly into the concrete filaments at 3 specific elevations: the 5th layer near the bottom, the 50th layer in the middle, and the 95th layer at the top. The data revealed a positional paradox. The bottom layers of the exact same wall exhibited significantly higher interlayer bond strengths than the top layers. The upper printed layers sat exposed at the top of the structure. With a larger surface area, water evaporates rapidly. Crucially, with no weight resting on top, this rapid moisture loss triggers unchecked early-age shrinkage. Down at the base, the environment is identical, but the mechanical reality is entirely different. The lower layers support the cumulative weight of the 99 layers stacked above them. That downward compressive force physically restricts the bottom layers, artificially limiting their shrinkage deformation. Elevation itself creates a mechanical gradient. Top layers are unweighted, shrink freely, and delaminate, while bottom layers are scaling into tight, monolithic bonds. To evaluate the theoretical baseline cracking tendency of the different concrete mixtures, researchers used the ASTM C1581 restrained ring test. Under laboratory restraint, mixture M.03 cracked prematurely at just 5.2 days. Mixture M.01 survived the internal stress buildup until 8.2 days. Those baseline tolerances dictate how the material behaves when deposited layer by layer on the active build site. This chart shows the peak microstrain recorded at the highly exposed top location across the different designs. Wall M.01 reached 788.4 microstrain. Wall M.03 peaked at 974.5 microstrain. That represents an approximately 24% increase in maximum shrinkage strain between the two formulations. That contraction incurs a massive penalty. In physical splitting tests, wall M.03 suffered a 29% reduction in interlayer bond strength compared to M.01. When a freshly deposited layer begins hydrating on top of an older, already setting layer, their rates of shrinkage are mismatched. That incompatibility induces shear stresses perpendicular to the interfacial plane. Internal microstrain data confirms what physical fractures suggest. Unchecked shrinkage physically shears the printed layers apart from the inside out before they fully set. The variance in shrinkage between these walls originates strictly from their chemical mix designs. The primary variable is the water-to-binder ratio. Mix M.01 uses a strict 0.30 ratio, while mix M.03 is much higher at 0.40. That higher 0.40 ratio introduces a high volume of unreacted mixing water into the concrete that is not consumed during the hydration process. The physical instability of that excess water is revealed during a 35-bar pressure bleeding test. At the microstructural level, as that excess bleed water evaporates, it leaves behind a coarse, highly porous network of empty capillary voids inside the concrete. As the matrix hardens, these empty capillary voids structurally collapse, driving aggressive volumetric contraction. This is drying shrinkage. The 0.30 ratio of mix M.01 avoids this. It forms a dense, tightly packed matrix with minimal free water, which significantly reduces internal stress. To achieve flowability without adding excess water, engineers increase the dosage of chemical superplasticizers. This provides the necessary viscosity without the severe shrinkage penalty. In 3D printing, where external physical constraints are absent, the internal capillary pore network becomes the sole governor of geometric stability. The failure sequence is a direct causal chain. High water to binder ratios lead to excess evaporation, driving extreme shrinkage microstrains and interlayer delamination. Across experiments, this relationship remained inversely proportional. Increasing the ratio produced a predictable drop in interlayer bonding strength. Perfectly balancing these parameters, as seen in the optimized M.01 mixture, creates a stable, cohesive structure. Removing traditional formwork effectively shifts the entire structural burden onto the material's internal chemistry and rheology. For additive concrete manufacturing to scale, engineers must treat shrinkage management as the foundation.